Have you ever actually wondered what's powering this massive modern AI boom we're living through? I mean, from chatbots writing entire essays in seconds to systems just magically generating hyper-realistic videos from a tiny text prompt, what is the hidden engine that's actually driving all of this? Well, welcome to this explainer. Today, we're demystifying the architecture that literally changed machine learning forever. We're talking about the transformer. We are going to break down exactly how this single mathematical model basically took over the world of artificial intelligence. And by the time we're done here, you're going to understand exactly how the engine of modern AI actually works under the hood. So here is our roadmap for today. First, the engine of AI. Second, the sequence bottleneck. Third, attention changes everything. Fourth, anatomy of a transformer. And finally, number 5, training the machine. Let's get right into it. Part 1, the engine of AI. So to really understand this, we need to acknowledge the massive shift that happened in generative models. It was a shift powered entirely by one specific neural network family, transformers. Now, the crazy thing is, this architecture just completely threw out older, super complicated designs to focus solely on something called a multi-head attention mechanism. So what does that actually mean for us? Well, instead of relying on all these convoluted pathways, this model simply converts text into numerical tokens and uses attention to contextualize the data. It basically figures out exactly which pieces of information matter most to each other, no matter how far apart they are in a document. Which brings us to part 2, the sequence bottleneck. Now, to truly appreciate this huge breakthrough, we kind of have to look back at the dark ages of machine learning sequence modeling. Before transformers came along, engineers relied really heavily on recurrent neural networks, or RNNs, and LSTMs. The catch? These older systems process data sequentially. It's like trying to read a massive novel through a tiny peephole, shifting it over just one word at a time. You read the, then you move to quick, then brown. It is just incredibly slow. Transformers, on the other hand, use parallel processing. So instead of that tiny peephole, the transformer is looking at the entire page all at once, taking in every single word simultaneously. It's a total game changer. And because of that sequential reading, those older models suffered from a major headache. It's called the vanishing gradient problem. Since they had to process text word by word, by the time they reached the end of a really long paragraph, they simply forgot the early parts of the sentences. The mathematical information just essentially faded away. And honestly, it gets worse. This sequential nature meant AI was hitting a massive computational speed limit. You see, modern GPU chips are designed to do thousands of calculations at the exact same time. That's the magic of parallelization. But if your algorithm forces the computer to wait for word number 1 to finish before it can even look at word number 2, you can't use the full power of the GPU. The whole system just creates this huge bottleneck. Enter part 3, attention changes everything. So in 2017, a monumental shift shattered this bottleneck forever. A team of Google researchers published a paper with this famously bold title, Attention is All You Need. And let me tell you, this wasn't just some catchy headline. It was a literal mathematical proof showing that those old, slow, recurrent neural networks were completely unnecessary for translation and language modeling. The researchers' brilliant solution was to give the model a bird's-eye view, contextualizing the entire sentence simultaneously through multi-head attention. By allowing all those tokens to be processed in parallel, the model could mathematically amplify the key signals, the really important words, and diminish the less important ones across these massive context windows. It learned how to weigh the importance of every single word against every other word in a sentence, all at the exact same time. It's just wild to think about. All right, part 4, anatomy of a transformer. Okay, let's pop the hood and reverse engineer exactly how this machine actually processes human language layer by layer. It starts with the literal journey of text entering the model through pre-tokenization and tokenization. Basically, this transforms a raw string of text into a sequence of distinct tokens. And by the way, tokens aren't always whole words. Sometimes they're chunks of words, syllables, or even individual characters. This is actually what helps the model handle unknown words or really complex terminology. Once it's tokenized, we move to embedding. Here, each token is converted into a high-dimensional vector. Think of this as translating a human word into this rich mathematical coordinate that the computer can actually calculate with. And finally, we arrive at positional encoding. Now let's pause here for a second, because this is a fascinating fix. If the model is reading everything at once in parallel, how on earth does it know the order of the words? This clever step is exactly how it magically remembers word order without reading sequentially. Positional encoding stamps each token with a fixed-size vector that represents its relative position. This ensures the network understands that man bites dog means something entirely different than dog bites man. Simple, but absolutely crucial. Next up, those tokens enter the attention mechanism, and we could de-jargon these highly complex query, key, and value matrices into a really intuitive parallel matching game between words. So think of the query as a word asking, hey, what am I looking for? The key is every other word answering back, here's the information I have. And the value? That's the actual underlying meaning that gets passed along when a query and key match up. For example, imagine the phrase, the bank of the river. When the model processes the word bank, it sends out a query. The word river has a key that essentially says, I am a body of water. When that query and key connect, the resulting value tells the model that bank means the muddy side of a stream, right? Not a financial institution where you deposit your checks. And this matching game is happening incredibly fast, across thousands of words simultaneously. But wait, if the model is trying to generate new text and it's processing everything in parallel, how do we stop it from cheating and just looking at future words? To prevent this, decoders use a really clever causal mask. Masked attention applies negative infinity to future tokens, cutting off those attention links completely. This mathematical trick ensures the model is only predicting the next word based on the past, completely preventing any reverse information flow during the generation process. No time traveling allowed. Which brings us to part 5, training the machine. Now that we understand how the anatomy actually processes data, how do we teach it to understand human language? Well, the standard paradigm involves 2 major steps. First up, you pre-train the model on a massive generic dataset. We're talking about a colossal scrape of the entire internet, using self-supervised learning. During this phase, it's just learning the general structure, the grammar, and the basic facts of human language. Second, you fine-tune it on a much smaller, task-specific dataset via supervised learning. And this is exactly how a raw generic text predictor transforms into something specifically good at being a helpful assistant, a specialized medical advisor, or even a software engineer. During this training process, models tackle different tasks to build up their intelligence. Masked models, like BERT, for instance, learn by predicting hidden tokens based on their surrounding context. It's basically playing a giant game of fill-in-the-blank. Then you have autoregressive models like the famous GPT series. These are trained to simply predict the next token sequentially, over and over again, stringing sentences together one word at a time. And finally, prefix LM models like T5 are given a specific prefix context or a prompt, and they're trained to predict what logical sequence of tokens should come right after that. And what is truly astonishing today is how this exact same text-based architecture is now being successfully applied across entirely different modalities. The transformer is no longer just for words, folks. It is the backbone of vision transformers powering computer vision. It drives state-of-the-art speech recognition for audio. It's the engine behind those incredible image and video generation tools like DALL-E and Sora. And remarkably, it's even being deployed right now to control physical movements in modern robotics. So, I'm going to leave you with this final provocative thought. The transformer was invented just a few short years ago to translate text. And now, it is taking over computer vision, audio, robotics, and it's even predicting protein structures in biology. So when this single mathematical engine finishes taking over all these domains, what happens next? What is the actual limit of the transformer? Thank you so much for exploring this fascinating architecture with me today, and keep questioning the algorithms that are shaping our world.